Professor Martin Brazier walks the galleries of the Oxford Museum of Natural History. He is the perfect stereotype of an Oxford professor. Shoulder-length white hair, tweed jacket patched at the elbows, and a mysterious stain on his once white shirt. The cabinets of the museum are arranged chronologically, and in his mind Professor Brazier can step back through time, mentally cloaking dusty bones with scales, feathers and fur to witness the transformation of planet Earth through geological eons as he walks the Victorian Museum. He is met first with the startling variety of life on Earth today. Multicolored birds take wing above mammals in the trees, reptiles on the ground, and fish in the water. Further back are creatures that thrived just a few thousand or million years ago. The dodo rubs feathers with the ancestors of modern horses and the lumbering woolly mammoths, while our own ancestral cousin Australopithecus stoops in the background. Stepping further back through time brings him suddenly to an age of mighty dinosaurs. A dynamic and varied ecosystem sees vicious tyrannosaurs stalk across the plains after armored ankylosaurs and miniature Compsognathus fleeing at their feet. Tracing the evolution of these terrible lizards further back into the Carboniferous, it is not animals but trees that rule the world. Towering forests of lycopods stretch the entire length of the Pangean supercontinent, while insects and amphibians still cling close to the water's edge. By the Devonian, 400 million years ago, the great diversity of life shifts from the land to the seas, as prehistoric fish of every conceivable size, shape and colour swarm the oceans. Deeper in time, the professor steps across another extinction, marked by a flash of glaciation, and the ocean creatures transmute into simpler, more experimental forms. Trilobites swim, crawl and burrow alongside tooth-shaped conodonts, the ancestors of vertebrates, and saw-like graptolites. Reaching 540 million years into the past, he is overwhelmed by an explosive radiation of experimental life. Within relative moments, the ancestors of every living group of animals appears. Sponges, corals, arthropods and worms all jostle for dominance in the early Cambrian seas. But even passing by this explosion of biological innovation, there are wonders to be found. Failed fractal experiments at multicellular life are rooted on the sea floor or inch across it through layered mats of algae and bacteria, leaving cryptic marks in the sand that will persist for 630 million years. And it is here that Brazier's flight of imagination is met with a wall of ice. A glaciation the likes of which the Earth has not seen since. The world-spanning Big Freeze persists for 100 million years, and beyond it, nothing more. The professor is brought back to reality with a bump. The museum is packed to the rafters with a dazzling variety of evolution and geological history that spans the best part of 1 billion years from the Neo-Proterozoic to today. But the events of the previous 1 billion years scarcely fill a single cabinet. Nothing, it seems, happened. Not just in the evolution of life, but also in the changing climate, continents, and oceans. With a hasty glance at his watch, Martin Brazier steps out of the museum and hurries across the courtyard to the Department of Earth Sciences next door. He is late for his lecture. Today, his students are eager to hear him talk on one of his favourite subjects, the dullest period in Earth history, when, apparently, nothing happened for 1,000 million years. But what was happening on Earth for all that time? And how could it stay the same for so long? It is a time that Brazier himself affectionately dubbed the Boring Billion. But could nearly a quarter of Earth's history really be so empty? This video is sponsored by CuriosityStream, the documentary subscription service. We here at History of the Earth are big fans of factual content. There's only so many times you can watch Squid Game before it's time you learnt about how weird real-life squid are. One great documentary we've been enjoying on CuriosityStream is The Kingdom, How Fungi Made Our World. Fungi are bizarre, with some of the largest and oldest organisms on Earth making up its alien kingdom. We'll be covering their origins soon, so this documentary is a great way to prime your knowledge. CuriosityStream is a bargain at less than $20 a year and has a wide range of documentaries on topics ranging from science to music, nature to sports, with new shows popping up every week. So head over to curiositystream.com/History of the Earth to sign up, and using the promo code History of the Earth will save you 25%, bringing a full year down to $14.99, just over $1 a month. Two figures labour up a rocky hillside in the wild country of Sudbury, Ontario. They are heavily laden with bulky rucksacks and more equipment than anyone could need on this summer's day. As they walk, they narrate their progress into microphones, commenting on the terrain, the rocks they see, and their interpretation of the landscape. It is a bizarre activity, but a necessary one for these two men. For they are John Young and Charles Duke. It is 1971, and in 8 months' time, they will be doing the same thing on the surface of the moon. This is a training mission for the two Apollo 16 astronauts with dummy equipment designed to imitate the heavy spacesuits that will keep them alive on their mission. But their primary goal is to analyze the rocks around them and learn to recognize the signs of meteorite impact when they see them. Because this lunar landscape, nestled to the north of Great Lake Huron, was indeed formed by an impact some 1,800 million years ago. The layered seafloor rocks on the barren hillsides have been shattered, melted and flung 800 kilometers from their origin, leaving behind a crater that was once 200 kilometers across. It is the third largest such crater on planet Earth, and the astronauts speculate that it was created by a space rock some 15 kilometers across, twice the height of Mount Kilimanjaro. Geologists believe this behemoth to have been an icy comet, which may have been flung inwards from the frigid outer reaches of the solar system many millions of years earlier. There are many unknowns surrounding an impact crater that has sat at the surface of the Earth for so long. But one thing is certain. This was the last exciting thing to happen to the planet for 1 billion years. The astronauts who trudge along the crater's shattered and deformed rim are only able to gather information with their eyes and cameras, but more sophisticated analysis of these and younger rocks will reveal concentrations of each element within them, and the proportions of those elements belonging to different isotopes. Carbon and oxygen, among others, both have light and heavy forms that behave differently under the various biological and physical processes. So by analysing the isotopic composition of the ancient rocks, geologists are able to reconstruct the average conditions of the time, including atmospheric composition and global temperature. And long after the Sudbury-trained astronauts put their knowledge to use on the moon, Earth-bound geologists were still piecing together the deep history of our own planet, using these isotopes. And in 1995, Harvard geochemist Roger Buick revealed unexpected results from the rocks of northwestern Australia that seemed to show a shocking pattern. The carbon and oxygen isotopes from between 1.8 and 0.8 billion years ago just stayed the same. He and his co-authors had examined the Australian rocks with high precision, and they reconstructed an isotopic timeline that simply flatlined. This was in sharp contrast to the isotopes of rocks both older and younger than these, which varied much more widely as a result of global environmental changes. But for this billion years, the elements in the rocks were unanimous. everything just stayed the same. This result was corroborated around the globe and was so remarkable that it prompted Buick to paraphrase Winston Churchill. Never, in the course of Earth history, did so little happen to so much for so long. $1.8 billion years ago, the Earth had barely emerged from the world-spanning Huronian glaciation caused by the emergence of oxygen-producing photosynthesizers in the oceans when the Sudbury Comet blazed through the skies to smash mercilessly into the Canadian Shield. But once the dust from this catastrophic impact had settled, the global climate remained remarkably warm, until a billion years later another tremendous glaciation gripped the planet from its poles to the equator. For a billion years between these gargantuan ice ages, Earth basked in average temperatures that were 4 degrees warmer than they are today. Summer days at the equator reached 30 degrees Celsius, while polar waters remained ice-free. Some sea ice may have formed during warm, wet winters, but there were no permanent ice sheets on the land or oceans. Geochemists face some difficulty in explaining such warm conditions at this point in Earth's history. At the beginning of the boring billion, the Sun is less than 2/3 of its current age and is some 15% less luminous, casting that much less light and heat across the void of the inner solar system to warm the planet. So it seems likely that the atmosphere contained gases that could trap that weak illumination and hold it close to swaddle the Earth to greater temperatures, as man-made greenhouse gases do today. But what were these gases? Carbon dioxide in the quantities needed to create such balmy conditions would have dissolved into the oceans to turn them acidic, but there is no record of this. Methane would have the power to warm the Earth with much lower concentrations, but since life is the only known source of sustained methane production, there is no record of the necessary bacteria in sufficient quantity to make the necessary impact. So geochemists invoke more exotic greenhouse gases. Nitrous oxide, which we know as laughing gas, may be one such component. If it were elevated to 10 times its modern natural levels, it could be enough alone to warm the Mesoproterozoic Earth and keep it warm for a billion years. Meanwhile, on the land surface, this vast period saw the reigns of 2 gigantic supercontinents, Columbia and Rodinia. Although no supercontinents have existed since the breakup of Pangaea 175 million years ago, geologists have nevertheless rewound the tape of plate tectonics to see continental masses drift together and break apart several times over many hundreds of millions of years. These so-called supercontinental cycles usually bring about global changes in ocean and atmospheric conditions, as the uplift of mountains and rifting of basins changes the pace of rock recycling worldwide. So it is surprising that a period of such stability during the boring billion encompassed the transition from one great supercontinent to another. Yet, the change from Columbia to Rodinia about 1.2 billion years ago was unlike any other supercontinental transformation. Reconstructions from surviving fragments reveal that Columbia only went through minor changes to become the new and improved Rodinia. Some regions rotated, some slid along the outer perimeter, but there was not the wholesale shattering and dispersal of fragments we would expect. Without extensive rifting or collision, a single contiguous landmass remained in situ across the mid-latitudes for a billion years. And with all the continental pieces gathered in one hemisphere of the globe, the rest of the world was given over to vast ocean. But it was a very different ocean to the one we see today, or the one that dominated through Earth's earlier years. Donald Canfield was a curious child, constantly hounding anyone who stood still long enough with questions about how the world worked. Taking holidays at a cottage in the Florida Keys, the Canfield family Donald, his father, and his grandfather would spend days fishing in the azure waters, and it wasn't long before the inquisitive young man would develop a fascination with the ocean. At the tender age of 13, he vowed to dedicate his life to the studies of our seas, and 40 years later was elected to the National Academy of Sciences, thanks, in part, to his revelatory theories on the ocean chemistry that turned the seas black during the Boring Billion. Earlier ocean sediments, dating to the time of the Great Oxidation by newly evolved photosynthesizers, are defined by widespread banded iron formations. These striped red and black deposits represent the pulsing oxygenation of the ocean, as that oxygen reacts with iron in the water to rain out red iron oxide all over the world. But during the Boring Billion, these formations are gone. There is no iron oxide being deposited anymore, and little evidence even of oxygen in the deep waters for 1 billion years. What happened to the global superocean all this time? Donald Canfield pieced together the evidence from billion-year-old rocks and modern-day ocean chemistry to paint a radical picture of a very unfamiliar ocean. Cold water flowing off permanent ice sheets today generates dense, so-called bottom waters that sink to the abyss and power a great circulatory conveyor to mix seawater between ocean basins and between the surface and the deep. But during the relative warmth of the Boring Billion, no such ice sheets could persist, putting a stop to cold sinking bottom waters and bringing the ocean conveyor to a grinding halt. The seas became stratified from top to bottom, with very different conditions in different layers, through the ocean depths. Canfield suggests in what has become known as the Canfield Ocean Model that instead of oxygen reaching the ocean depths to stop the formation of banded iron formations, it was the presence of another compound, hydrogen sulfide, that blocked the creation of these distinctive layers in the deep ocean. The warm surface waters lit by the sun and able to exchange gases with the atmosphere are still full of oxygen and oxygen-loving organisms. But at greater depths there is a sudden change to stinking sulfidic waters, driven in part by bacteria that colonize the boundary to convert sulfate to sulfide where oxygen concentrations are too low. Hydrogen sulfide, the gas responsible for giving rotten eggs their distinctive smell, fills the ocean depths and reacts with iron to make pyrite, fool's gold, instead of red-banded iron oxide. And so the sea floor is covered with a stinking black sludge that turns the entire ocean dark. This stagnant superocean persists for the duration of the Boring Billion, and suggests that oxygen levels after the Great Oxygenation event may not have been as high as we once thought. The oxygen lovers that brought about their own destruction now only cling on in a thin surface layer of mere meters, atop a reeking, fetid murk many kilometers thick. It may sound inhospitable, but life, as it so often does, finds a way. Slow weathering from unchanging continental masses and low atmospheric oxygen means that few nutrients are delivered to the seas, so there are not enough essential minerals to sustain life throughout the oceans. Nevertheless, along the shores of the eternal supercontinent, there is enough for microbial life to scrape by. But it is still an ecosystem dominated by the simplest kind, prokaryotic bacteria. 2 billion years after they emerged, these bacterial cells are still the masters of the Earth. They may be simple, but they are by no means the same. Different bacterial metabolisms allow communities to thrive in the varied geochemical zones of the Canfield Ocean, and reinforce it in turn. But the stagnant oceans of the Boring Billion gradually become depleted in one element that is essential for all life: nitrogen. Some bacteria have the ability to extract and use nitrogen directly from the air, but it is the lack of this bioessential element that holds back the rest of evolution. Paleontologists believe that the more complex eukaryotic cell had already emerged before the boring billion began, but compared to the proliferation of bacteria after their first appearance, the eukaryotic revolution struggles to find its feet. Their greater complexity makes for greater need, and so they can only thrive where there is a chemical bounty on which they can feast. There are rudimentary food webs. Large protists are the apex predators, hunting down mindless herds of bacteria. In places, the eukaryotes begin to form rough, multi-cell associations, but for the most part, they are rare individuals among a thriving multitude of simpler forms. And that multitude is beginning to find its way out of the oceans too. Sustained by rainfall and wind-blown dust, the first cyanobacteria mats begin to colonize fresh water and terrestrial habitats. For the first time in Earth's history, there is the glimmer of green on the land itself. The world that persists for 1 billion years of the Mesoproterozoic is, by all accounts, an unpleasant one. A hot, steamy atmosphere is sustained by laughing gas. The land surface hulks immobile on one side of the world, while the ocean marches across entire hemispheres, uninterrupted by islands or ice. That ocean is a stagnant, putrid expanse, rimmed with black sludge and emitting a sulphurous stink that spans the globe. Living things are still microscopic, held back and ghettoized by geochemistry. An extraterrestrial visitor at any point in this period would be forgiven for turning back. And these conditions persisted for 1 billion years. And so, it has taken scientists the last 25 years to uncover just how so little could happen to so much for so long, and why things did eventually change. If a year ticked by each second, then all of written history would fit into a little under an hour and a half. Homo sapiens themselves have been around for 3.5 days, and it will have been 2 years since the extinction of the dinosaurs. On this timescale, the entire history of the Earth would span 140 years, and the boring billion, throughout which the Earth and life stood still, would last 31. 22% of the entire history of the Earth is defined by stasis. In this time, had it occurred in a more recent, more normal era, humans could have evolved from boneless sea creatures twice over. There could have been 2 or 3 traditional supercontinent cycles, and several hundred switches between icy and balmy climates. But there was not. These are fluctuations that define the more recent and familiar geological epochs, but there are no fluctuations to mark the passage of time through the boring billion. Only the inexorable and imperceptible advance of years. If fluctuation and variability is the norm, then the constancy of the Mesoproterozoic is an exceptional state that requires an exceptional explanation. All of Earth's systems are interconnected, so changes in any one component have the capacity to transform the rest and affect conditions worldwide. So perhaps the remarkable stagnation of climate, continents, atmosphere, oceans, and life needs only one driving factor. One major obstacle to change that keeps the rest of the planet in a rut. Geologists suspect that the giant spanner that brings Earth's surface processes to a halt lies not on the surface itself, but underneath it. Even 2.7 billion years after the planet's formation, its interior is still surprisingly hot. Heat left over from the violence of its accretion, plus the radioactive decay of heavy elements trapped in the core, contribute to an internal furnace whose swelter has no escape. The entire mantle is superheated, and the asthenosphere, the semi-solid layer that solid crust essentially floats upon, is especially torrid. Even though the Earth has cooled enough for mantle currents to begin to jostle the solid plates of the surface, this still isn't the plate tectonics that we recognize. When colliding plates are subducted beneath one another, they pass through the hot asthenosphere and are melted to a viscous shadow of their former selves, before they plunge too deeply. There is no descending slab inside the mantle to pull the rest of the plate down after it, and without this gravitational tug, the rest of the plate stays put. It is a process mirrored in millions of teacups across Britain every day. A dunked biscuit soaked too long in hot tea will lose its lower half to the depths of the cup, while the undipped portion still floats in place. And so, without the pull of a subducting slab, the plates of the Columbian and then Rhodinian supercontinents simply didn't have the energy to tear themselves apart. The land surface stays the same, and, as a consequence, everything stays the same. With no new rifts or mountain ranges, there is no new rock exposed for weathering, no new sources of nutrients or drawdown of reactive gases. No movement of the landscape to promote glaciation or change in sea level to offer fresh habitats for burgeoning life. The carbon cycle slows to a trickle and is stuck. Another surprising extraterrestrial factor may have also helped to dampen any fluctuating feedbacks in the Earth system during this time. Usually, when climates begin to warm, they see more evaporation from ocean surfaces, leading to greater cloud cover which blocks incoming sunlight to help reverse the initial warming. But there is another source that has been linked to the formation of clouds. Cosmic rays. As powerful beams of radiation cross space and bombard our planet, they help to create the seeds around which clouds form. So more cosmic rays leads to more clouds around the Earth. The effect is small enough to be masked by normal fluctuations in global weather and climate. But over a cosmic timescale, like the boring billion, these celestial forces have a chance to shine. Astronomers believe that the Mesoproterozoic coincided with a period of very low star formation in our galactic neighborhood, as a result of our movement between the Milky Way's spiral arms. Fewer stars being formed makes for fewer cosmic rays and, as a result, fewer clouds. The Earth's natural feedback to continually warm climates is, for this eon, crippled by galactic events. And so, it remains for 1 billion years. The only hope of escape from this interminable rut is the cooling of the planet itself. Heat from the interior radiates out into space at a leaden pace, and eventually the superheated asthenosphere cools. When subducting slabs can stay cool and attached to the plates on the surface for longer, plate tectonics shifts into a new gear. With more force behind them, they have the strength to pull apart, and Rodinia shatters. Compared to the languor of the preceding 1 billion years, the planet transforms in a geological heartbeat. Continents scatter, the ocean basins are reformed and mixed, the composition of the air transforms, and the climate cools. For the first time in an eon, permanent ice persists throughout the warmest summers, and before long, that ice stretches almost to the equator. The tedium of the boring billion is broken, and Earth and life erupts into frenzied change once again. It is important here to remember a central tenet of scientific reasoning. The absence of evidence does not necessarily translate to evidence of absence. The fact that scientists haven't found human-like neural circuitry for pain in animals like fish doesn't necessarily mean that fish can't feel pain. The absence of any contact from extraterrestrial civilizations doesn't necessarily mean that aliens don't exist. And so, just because we don't find evidence of change during the boring billion, doesn't necessarily mean that change didn't happen. Simon Poulton was a young PhD student at the University of Leeds when Roger Buick and Martin Brazier are uncovering the truth of the boring billion. Taking a break from his field studies into the stinking black mud at the bottom of modern-day oceans, he attended a European geoscience conference in Vienna. Topping the bill for the day's talks was Donald Canfield, with his theories for a stinking black ocean that persisted for 1 billion years. And now, more than 20 years later, Professor Poulton is head of geochemistry and Earth history at the University of Leeds, having travelled with Canfield to the northern shores of Lake Superior and finding evidence to support the stinking Canfield oceans. But he also uncovered an even more important truth. The boring billion wasn't actually that boring, after all. His studies into the ancient rocks of this period revealed that oxygen levels in the oceans, while low, did in fact fluctuate over more familiar geological timescales. Not only that, but the seemingly hard stop in the development of life is blurring at the edges as paleontologists uncover more and more fossils dating from this once barren period. Frenzied activity of more recent Earth processes has done an excellent job of obscuring the true record of the past. Rocks that are nearly 2 billion years old are scarce, and those that survive have been buried, crushed, cooked, and deformed. It takes the tenacity and expertise of specialists like Simon Poulton to extract the truth from such an altered and fragmented record. Now he, and many other Mesoproterozoic experts, have had 2 decades of staring at the dullest time in Earth's history, and they have found the boring billion to be just as exciting as any other era. There is, for example, evidence of volcanic activity. The upwelling and outpouring of magma in the Australian and Canadian shields led to the formation of brand new land surfaces and reconfiguration of the Rhodinian coastlines. Plate tectonic movements may have been stifled, but they weren't absent entirely, and the collision of continental fragments saw the creation of mountain ranges to rival the Andes. The scars of the Grenville orogeny still cut across the American continent, from Mexico to Labrador, and extend across the Atlantic into Scotland. The climate may not have been as unvaryingly warm as was originally thought either. The transient nature of ice does not necessarily lend itself to leaving permanent records in the rocks, and when these rocks have been so racked by time, any event smaller than a global ice age could be missed or erased entirely. In fact, as recently as 2020, evidence of debris dropped from rafted icebergs was discovered in 1 billion year old lakebed rocks from Scotland. So there was ice at this time, and we will find hints of it if we know where to look. As for life, there is no denying that eukaryotes didn't take off at the speed of their bacterial cousins. But there appears to be more variety out there than paleontologists assumed 20 years ago. Like the transient ice, small-scale cellular organisms are vanishingly unlikely to leave a trace in such ancient rocks. Fossils of multicellular algae, several tens of centimeters in length, have been recovered from Chinese rocks more than 1.5 billion years old. Fossils of complex eukaryotes have been found in the same billion-year-old Scottish lakes as the iceberg dropstones. There is complex life out there if we know where to look. And in fact, the relative stability and toxicity of the boring billion may have been exactly what these more complex cellular organisms needed in order to take the stage. Eukaryotic cells first came about when 2 prokaryotes contrived to collaborate, with one coexisting inside another so that both parties reap the benefits of their specialist skills. But modern eukaryotes contain much more complexity than the simple cooperation of 2 bacteria. They contain intricate machinery and interreliant processes whose evolution is harder to explain. But with 1,000 million years of unchanging conditions, these new cells have a chance, through low-stakes trial and error, to sort things out. While the abundant prokaryotic masses keep the balance, eukaryotes can experiment and figure out the elaborate dance of sexual reproduction. So, at first glance, the vast span of time between the Sudbury impact 1.8 billion years ago and the global ice age 0.8 billion years ago certainly seems to be uneventful. But even as Professor Martin Brazier named it the boring billion, he didn't really believe it was dull. He was fascinated by it, and inspired a new generation of geologists to be fascinated by it too. Although nothing appeared to happen from one long moment to the next, the world that emerged at the end of the Boring Billion was very different to the one at its start. Unprecedented geological stasis was the necessary calm before the evolutionary storm, priming the machinery of Earth and life for the explosive change that was to come. We may have never evolved without it. You've been watching the entire history of the Earth. Don't forget to like and subscribe and leave a comment to tell us what you think. I will see you next time.